So I'm supposedly talking about all of economics, according to the title of my talk, but I thought I'd specialize on the most important parts. I'm going to tell you a little fable about food hoarding. It's kind of in the tradition of Aesop and Walt Disney. We've got animal characters, but the truth is I have somewhat more ambitious intentions about who it might apply to. Slightly differently from Aesop and Disney, I want this to have something that's really true about the real animals and might be instructive as well. So the question is, what can evolution tell us about the preferences towards risk? And actually, I'm building on some work done by another fabulist a little later than Aesop and Disney. You may have heard of this guy. Robson wrote an article in 1996 that formalizes some things that biologists have known for quite some time. But essentially, he has two conclusions. For idiosyncratic risks, evolution's going to select animals that essentially maximize arithmetic mean reproduction. But for aggregate risks, for risks that affect the entire population, at least of specimens of any gene, the prediction is that these animals would seek to maximize the geometric mean survival probability. And we'll see what that means in an example. I think maybe this example, I think, is well suited for giving you some flavor of this notion and why I think it's quite important. So here's our little story. I started thinking about this some years ago when I lived in Ann Arbor, Michigan, and you would watch the jolly little squirrels gathering nuts to survive through the winter. But of course, gathering nuts is costly. The more you do, the more you subject yourself to risks from Buicks and cats and things like that. And squirrels don't know how long the winter is going to be. At least I don't think they do, or at least I wondered. Oh yes, I'm out of my cage. At least I wondered how do they decide how much nuts to collect for the winter? And so one possibility is, I thought, was, well, let's think about what evolution would do. So here's a little model, very, very simple model for starters, and to give us some intuition. Then we'll try slightly fancier models. So imagine that there are just two kinds of winters, short ones and long ones. And there's an IID probability distribution with some probability p. There's a short winter, and some probability 1 minus p. There's a long winter. And for the moment, there's no information in history about patterns. So you don't know, it's going to be short or might be long. And then, of course, there are two reasonable strategies for squirrels. You could either store enough nuts for a long winter or store enough nuts for a short winter. And now the probability of surviving the predators is going to be something. If you do the short winter strategy, it won't be so high. If you do the long winter strategy, you subject yourself to extra risk of being eaten, and so you will have a survival probability 1 minus the hazard rate times the survival probability if you did the short strategy. So squirrels will survive and reproduce if and only if they are not eaten by predators and store enough for the winter. If the winter's short, then of course a short winter squirrel will survive with the probability it will survive so long as it evades predators. And a squirrel with the long winter strategy, well, he'll have plenty of nuts too, but he'll have a lower probability of surviving because he's exposed himself more to predators. So, but if the winter's long, the short strategy squirrels are goners, and the long strategy squirrel, he'll make it through the winter if he survived while gathering the nuts. So that's the setup. Yeah, okay. This is a G-rated lecture. I'm not going to, I'm going to follow the guidance of Disney and Robson, who are noted prudes. And we'll suppose that your strategy is inherited from your just one parent. So a squirrel reproduces at the rate rho if it survives through the winter. And so it doesn't matter what you did. If you make it through the winter, you'll reproduce. So now, of course, the first thing you think about when I first thought this was kind of fascinating is, well, if the only strategy you could use was a pure strategy, it's pretty obvious that you're going to get left with a population only of long winter strategists, because the short winter ones will get wiped out. And in fact, part of Arthur's work shows that even if there's a low mutation rate, the mutation selection balance would still have you with almost entirely long winter squirrels. But that somehow seems unsatisfying to me, because notice that answer is true no matter how rare long winters are. And so economists, are always looking for things to work out efficiently, and we even kind of complain, we're even inclined to look at Mother Nature and wonder if she isn't more clever than that. So what we might consider, and in fact this is an idea that biologists have had for some time, is how about a gene that randomizes the instructions that it gives to the squirrels that carry it? So such a gene would essentially diversify its portfolio of animals that are carrying it around. And it would have some short winter strategists carrying it around and some long winter strategists carrying it around. And in general, it's going to be true that a gene that does this with appropriate probabilities is going to outperform either of the pure strategy genes. Probably not surprising. So what we're imagining, of course, is that somehow there's, well, I mean, abstractly, you could just think of a gene that breeds true that flips a coin with some odds and makes you do the long winter or the short winter strategy. Or we could, of course, have it that there's some random process, physical process that you run into that triggers whether you become a long winter or short winter squirrel. But either way, we'd have squirrels with the same genetic makeup acting differently. So imagine then we got this randomizing gene that tells its squirrel, with some probability it tells its squirrel to do the long winter strategy, and some probability tells its squirrel to do the short winter strategy. And so now the survival rate of a squirrel carrying this gene, okay, the expected number of descendants that this gene is going to have will depend on whether, over the course of the next winter, will depend on whether it's a long winter or a short winter. If the next winter happens to be short, then with probability pi s, the gene tells its squirrel to do the short winter strategy and is subjected to Vs predation risk. And with probability pi l, it tells its squirrel to do the long winter strategy and is subjected to the greater hazard VL. And so this is the probability that a descendant of this, or a squirrel carrying this gene, will survive a short winter. If the winter is long, well then of course the only chance that the gene gets passed on is if the squirrel happens to take the long winter strategy, which happens with pi L, when taking that long winter strategy, of course, it's exposed to the higher predation rate, VL. And so these are the survival rates in short and long winters, respectively. Now, let's consider the long-run reproductive rate of a gene that randomizes with probability pi. Okay. So consider just a period of, say, a long period of t years. If that period of t years had k short winters and t minus k long winters, then over the, remember, reproduction is multiplicative. So you'll have, you'd have, if we started out with a series, for example, if we started out with a series of k short years followed by t minus k long years, we'd have the short winter strategy to the k, survival rate to the k, long winter strategy, survival rate to the t minus k. But of course, it doesn't matter. I mean, it doesn't matter. That same argument is true no matter what order those short and long winters come in. And in the, okay. And so, and then of course the average annual growth rate, this is the total growth over t years. The tth root of that is the average annual growth rate, and that looks like the following. And you can probably guess what's the next claim. So by the law of large numbers, as t becomes big, the fraction of short winters will become very close to the probability of a short winter on a single trial. And so the long-run average annual growth rate becomes this simple geometric mean. That should be a P sub S and a P sub L. So the claim is that the evolutionary process would result in a population of pi strategists where pi maximizes this particular geometric mean of survival rates in long and short years. So now the highest long-run average growth rate, that's going to be maximized when, here I'm taking the log of the long-run average growth rate. Just because it's boring to write those little exponents. Of course, when you maximize the log of something, you're also maximizing the sum. When you're maximizing something, you're also maximizing its log, and it's a little handier to write it like this, and that seems to be a common practice. It maximizes this subject, of course, to the constraints that your pi is a probability distribution, that you have the probability that you do the short winter plus the probability that you do the long winter strategy has to add to 1, and most of those probabilities have to be at least 0. So now, in fact, let's see. So let's just take a look at what the answer turns out to be. So if the probability of a long winter is smaller than the hazard rate of gathering enough food for a long winter, given that, suppose you've already gathered enough food for a short winter, now you consider, should I gather enough food for a long winter? There'll be a hazard rate. There will be some probability I'll be eaten when I do that. And the question is, suppose the probability of a long winter is smaller than that hazard, okay, then the solution is going to be that my optimal strategy is to gather enough nuts for a long winter, or the gene says, randomize what your squirrels do so that with probability PL over PH, they gather enough for a long winter, and with the rest of the probability, they gather enough for a short winter. when they do that, just using our little calculus for what are the survival probabilities that correspond to these, the survival probability of short winter squirrels is PSVS, and that of long winter squirrels is that. And the ratio of long winter strategists who survive, okay, yeah, the probability, the ratio of the probability that squirrels survive the long winter compared to the probability that they survive the short winter. Of course, that number has to be smaller than 1, and that ratio turns out to be what you see there, which will be smaller than 1 if and only if PL over H is less than 1. In the case where a long winter is more probable, the long-run growth rate is maximized by the pure strategy, which is store enough for the long winter. Obviously, it is not going to make sense to never store enough for a long winter. If long winters are very frequent, indeed, in this little 2-winter length model, indeed, you would always store for a long winter. So we can look at some kind of simple qualitative implications of this. So first of all, is if winters are rare enough and food gathering hazardous enough, the most successful strategy is a mixed strategy. There's a kind of probability matching here. Notice that the probability that you do the long winter strategy is proportional to the probability of a long winter. And of course, and also inversely proportional to the hazard of doing it. So, for example, if squirrels were as simple as this, and you were a squirrel biologist, you might test this theory by saying, well, let's look at the let's compare the die-off rate in harsh winters, say between northern Minnesota and Iowa. Okay, and so since the claim is that the die-off rate in harsh winters is inversely proportional to the frequency. So in fact, in places where harsh winters are more frequent, you'll see a lower die-off, not very surprising, a lower die-off rate because, of course, squirrels have been saving up more. Not so surprising, but it's kind of neat to see that it's, in fact, just a proportional relation. Another thing that's, in a sense, more striking is that in this case where the mixed strategy is called for, it's going to be true that if squirrels were simply selfishly trying to maximize their own survival probability, then indeed the short winter strategy has the higher survival probability. And it's in the calculation, but we could see it another way. You're a squirrel, you've now collected enough nuts for a short winter. You're trying to decide, should I collect some more to last for a long winter? Well, you say, if I do, then it's true if there's a long winter, I'll survive, but it's also true I'll face this hazard of getting eaten by a cat if I spend this extra time gathering. So my cost of gathering for the long winter after I've done for a short winter is H. And what's my benefit? Well, my benefit is that if it happens to be a short winter, it doesn't do me any good to gather the extra nuts. If it happens to be a long winter, it'll save my life. And so we compare those two probabilities. Now, anyway, so what we see is that the prediction is that you wouldn't get squirrels to act properly if you simply motivated them to maximize their survival probability. Okay? Some of them are doing things. You have to have some way that some of them are doing things that do not maximize their survival probability. In this case, they're gathering too many nuts from a selfish point of view. Okay, we can generalize this idea, or this little toy model, we can generalize fairly easily to the case of many possible lengths of winter, and we maybe see a little more of the structure when we do that. So imagine that the winter could last anywhere from 1 to W days. When I first thought about this, I thought that W had to be some number smaller than 365. I once talked about this in an audience where there was a Finn, and he explained that there was a year in Finland when there was essentially no summer, so no farmers could not plant for the entire year. So I suppose we could, and in fact, as you might guess, partly in my back of my head, I'm thinking of these squirrels as in similar situations to peasants gathering food for a long winter. So now the gene is going to choose a probability distribution of what instructions it gives its squirrels. And we'll suppose pi sub t is the probability that it makes its squirrel store enough nuts for t days. And let's suppose I'll do a little bit of simplification. I'll suppose that the probability of avoiding, that there's constant hazard. Every additional day's worth of nuts that you gather exposes you to a hazard h. And so here would be your probability of avoiding predators if you set out to collect t days of food. And again, we'll have these st of pi's are the expected survival rate of squirrels of a pi strategist gene if the winter is of length t. And so again, we'll do this exercise of finding the maximum. Let's maximize the geometric mean survival probability, or the log of the geometric mean survival probability, subject to the constraints that the probabilities add to 1 and are at least 0. Now, what you'll notice in this model, okay, if the winter is of length t, you're going to survive if you have collected at least enough nuts for t, okay? And there are several ways you could do that. You could collect exactly t days nuts or t plus 1 days nuts and so on. And the survival probability is just the sums of these probabilities that you collect so and so many days nuts times the probability you aren't eaten by a cat when you're collecting it. And then it turns out that the mathematics of the formula of the problem is simplified if we rewrite it as a function of the survival probabilities. And in fact, from this, there's a one-to-one correspondence between these STs and the pi's, because the probability that the probability you survive, let's see, well, just look at the algebra here. So pi t is the difference between the st and st plus 1 divided by vt, and so on. And so we can rewrite this formula, restating the pi's in terms of the s's. And when we do a little bit of algebra, it works out like that. And of course, we also need each of the pi's to be non-negative, so it has to be that the s's are increasing from, let's see, the s's are decreasing as time gets longer. As the winter gets longer, you're less likely to survive. Okay. So now have a result that if the distribution of winter's length is log concave, which, for example, a binomial distribution would have that property. Almost any of the familiar most of the familiar parametric distributions have that characteristic. So for example, if we just discretized a normal distribution, it would have this characteristic of being log concave. Anyway, it'll have, so one thing about log concave is they'll be single peaked. They'll be unimodal. So if that's the case, then there's going to be some minimal amount of nuts that every squirrel collects at least that amount. Every squirrel collects at least that amount of nuts, and of course some collect more. And we can then calculate what the survival probabilities are and what the probabilities are of each of these levels of nut gathering. And let's see. Well, it's not very exciting to look at them. We could qualitatively think. So there's a bunch of them that gather. Yeah, there's a bunch of them that gather at least W star, that gather W star nuts. And then there's a few more that gather one more day's worth, and a few more that gather one more day's worth. And they get fewer and fewer, running all the way down until finally there is a very small number of squirrels who gather enough for the longest possible winter. So why the assumption of log concavity? Well, we need it to be that the constraints require that when you look at just the abstract maximization problem, you need the constraint that the S's decline. If we had an interior solution, it has to be that the ratio of the S's are the ratio of the P's times 1 minus h. If the distribution is log concave, this ratio of the P's is always decreasing in t, and so there'll be exactly one level of length of winter such that pt plus 1 over pt times 1 minus h is, let's see, is smaller than 1, is bigger than 1 for less than that, and smaller for greater than that. So that, in fact, is what the solution looks like. So in this solution, then, there's this threshold amount that everybody collects at least this amount. By the way, let's see, yeah. Okay, well, that's all right. There's this threshold amount. Beyond this threshold amount, in fact, the longer the day, let's see, beyond this threshold amount, fewer and fewer squirrels collect nuts for more and more days. So in fact, the survival rate of squirrels who collect for t days is written there. Now notice what's going on. As we're going out to very long winters, we've got an ordinary distribution, the probability is falling. So more and more extreme winters become less and less likely. So PT is falling over this period. In fact, it must be falling over this period under my assumptions. And but this number ST is also falling because it's multiplied by something less than 1 to the power t. So we've got survival rates are falling with worse and more extreme winters. In fact, they're falling at a rate even faster than the frequency of these extreme conditions. So one question, of course, one might ask is this kind of theorist fantasies, or do animals really behave like this? Do we see this in nature? And the biologists have some interesting examples where it appears that we do see randomization, and in fact, biologists have often explained it in this way. For example, there's the famous work of Levins, who explains that that the seeds from a given plant will have varying lengths of dormancy before they sprout. Okay, and so they, as far as one can tell, they're genetically identical. They carry the same heritage, but they act differently. And this makes, you can see, this makes a lot of sense for a lot of plants, because if it happens that you get an early rain, it would be great if that rain continues and you come up right on time and you'll prosper. But it might be that the rain is a false start, and plants that come up then simply wither. And if, in fact, all the seeds behaved in the same way, early starters would be wiped out. But if, in fact, you diversify your portfolio by having some seeds germinate early and some later, you can escape this problem with essentially the same logic that applied to the squirrels. There's also some nice stories about these guys, the spadefoot toads. So I think their eggs are laid in vernal ponds, and sometimes these are highly variable environments. Sometimes the pond will dry up, sometimes it won't. Let's see, how does it go? I think that so there's two morphs of these guys that seem to carry the same genes. You may turn out to be a vegan, in which case you grow slowly, but you turn out really big, and that's a good strategy if your pond doesn't dry up. But sometimes your pond is going to dry up, and there's another strategy, which is the carnivorous strategy. In fact, meat eating is particularly interesting strategy here, because the meat you eat is your brothers and sisters. Another example is there's quite a lot of evidence. Apparently, guys go and dig up the hoards collected by various animals that store things, hamsters and squirrels and pikas, and somebody's done this in a lab as well to see how much they store. And there's a great deal of variance in how they behave. So another question we might ask is whether gambling is better than sex. Sex can provide variation too, right? Well, this model says it is. So you could clearly get variation by having, say, a sexual diploid population with a recessive gene for strategy S, say. And then this would show up sometimes, but not other times. You'd play a mixed strategy. But the weakness is that the strategy proportions you'd use in one year would depend on what kind of year you just had. Because if you've just had a harsh winter, then the genetic makeup of the population is going to be the only S short genes will be hidden in recessive copies, and the proportion of the short gene will be diminished. But if it's an IID process, you want to bet with the same odds every year. Now, even if the process weren't IID, suppose it were Markovian somehow, and you could the parent could observe how long a winter he's just survived through, and then decide how to randomize. Okay, even then, you would do something like we did. It's just that you would alter the probability distribution depending on what you've just seen before, and we'd have a Markov process. But it wouldn't look like what would happen with just plain sexual reproduction and dominance and recessiveness. Okay, I want to talk about one other possibility is there's another, you could imagine another way in which a gene could diversify the holdings of the squirrels that carry it. And that would be, well, you could imagine a thought experiment. Just suppose you somehow induced all the little guys that carried the gene to deliver their squirrel to work the same number of days, bring in the same number of days nuts, put them in a pile, and then you randomly redistribute them. Now, that wouldn't be a plausible process, but something a little like that might happen, say if squirrels can steal from each other, or more elaborately, if they could go to casinos and gamble and wanted to. Now, in fact, of course, I'm thinking about some of these other animals that don't have the nice bushy tails and are very poor at scampering from tree to tree. And some of these other animals are, in fact, able to reorganize, to redistribute by gambling. And, of course, both our species and squirrels sometimes manage to redistribute by means of theft, I think. So this is photographic evidence that squirrels do redistribute. So this is kind of a straightforward mathematical question, is if the gene could redistribute, could arrange to diversify, not by means of having different guys work with different intensities, but have them all work the same, and then randomize the distribution, what would it do? In fact, I think we can that if it were able to do that, it could reproduce faster than reproducing by having different guys work with different intensities, because, in fact, working at different intensities is a rather inefficient way of redistributing. The expected number of nuts that you collect there's going to be an optimum amount. The more you gather, the more you get, but the less likely you're to get it, and there's going to be some interior solution that would get you the most expected nuts. And in fact, a gene that commanded everybody to gather this optimal amount of nuts and then redistributed, subject to feasibility. And feasibility would be, well, let's see, you've got n guys each collecting y days nuts. Okay, so if you gave one nut to n1 people, that would use up n1 nuts, and if you gave 2 nuts to n2 squirrels, that'd use up 2n2, and so on. The budget balance is that, and that's equivalent to the expected number of nuts. It's a lottery where the expected number of nuts you give is the number submitted. So when we maximize that problem, it turns out that we can again do this little trick of rewriting it as a function of the survival probabilities. The problem then looks like this, and when you maximize it, you find out, well, if the distribution of winter lengths is unimodal, so there's one most frequent kind, and then it falls off this way, and falls off this way, and so on, then what's going to happen is there'll be some critical number of days such that, well, there's two possibilities. Yeah, there's some critical number of days such that nobody gets between 0 and that critical amount of days. So nobody be gathering small amount, tiny amounts of nuts. Now, if okay, yeah. Now, if so, one possibility is that let big PM be the probability. Oh, let's see. No, okay. Let little m be our critical amount of nuts. Okay. The nature of the solution is going to be then that if everybody gets, well, at least if enough is collected, everybody gets at least some minimal amount, PM, which is going to be something smaller than the average. Everybody's sure to get some amount, but it'll be less than the amount you're assured of is less than the amount that you would have brought in. On the other hand, so some guys are going to get screwed. They're going to wind up with fewer nuts than they brought in. Some guys are going to wind up with more nuts than they brought in, because we've got to have somebody, remember, who's got enough nuts to last the whole longest winter. And so there's a distribution that looks kind of like that. Now, what I had thought to do, but I, in fact, didn't get around to doing it. Well, what I thought to do but didn't get around to doing it was to draw a graph with the distribution of income and to calculate, to relate this to the literature on Gini curves and so on. You can essentially, you see this particular theory predicts a distribution of income. And now it's a distribution of income under rather very, very structured description of probabilities and payoffs and so on. But something like this would apply in much more general models. There's going to be a prediction of the distribution of income that would coincide with the highest long-run average reproductive rate. So now we